Okay, hi everyone. Welcome to our webinar today. This is our first webinar for 2024, so welcome back to our webinar series and one of the publicly available ones. So welcome to everyone who's maybe not so familiar with HILT. So my name's Jenny Selway. I'm the CEO of HILT CRC, and we're here to talk about the Net Zero Australia report and infrastructure needs for heavy industry. But I'd like to start off by acknowledging the traditional owners of the land. So I'm dialing in from Melbourne today. I'm the Wurundjeri people of the Kulin Nation, and I pay my respects to elders past and present, and also emerging, but also respecting that people are dialing in from all over Australia today, and even some international people dialing in as well. And so pay respect to the traditional owners of the land from wherever you're from and from wherever you're calling from. We are recording the webinar today, so just be aware of that, and we will be able to send the link out afterwards. So HILT CRC, for those people who aren't aware, is a cooperative research centre focused on heavy industry decarbonisation, and specifically iron ore, steel, alumina and cement sectors. So we're very interested in all of the reports that are and work going on at the moment that aim to map out decarbonisation pathways for the heavy industry sector. And the Net Zero Australia report did just that, looking at mapping out various pathways for net zero to reach net zero emissions by 2050. So joining us today is Associate Professor Simon Smart from the University of Queensland. And Simon is a project leader of the Net Zero Australia project, which is also a collaboration with the University of Melbourne, Princeton Uni and Nous Consulting. Simon's research is centred around sustainable production of energy and chemicals, including the development of enabling technologies and processes for the production of clean energy, materials and water. And so of particular relevance to the Net Zero Australia report for heavy industry is a scenario that was conducted looking at the onshoring of heavy industry, with specific focus on onshoring processing of iron ore and bauxite, and domestic production of iron and aluminium, and iron and steel and aluminium using clean energy, which was progressively displacing exports of iron ore, bauxite, alumina and fossil fuels. So Simon will take us through the overview of the Net Zero Australia report and also that specific onshore processing scenario. And then at the end of his talk, Gus Nathan, our research director, will join Simon for a Q&A panel. So please pop your questions in the chat and we will get to them at the end of Simon's talk. But for now, that's all from me, and I'll pass over to Simon.
Thanks very much, Jenny. Welcome to everybody, and let me share my screen, and hopefully that now looks okay. Have I got a thumbs up there from someone? Hopefully you're all seeing my screen. So yes, thank you. Getting straight into it. So this is the Net Zero Australia report. Was a study that looked at analysing the net zero pathways, reflecting the boundaries of the Australian debate. And there are a couple of things that made it unique in the overall scheme of net zero studies that are out and are coming out at the moment. One was that we focused on both the domestic, or I guess the national economy, as well as all of the emissions associated with the export of our fossil products. So if it came from Australia, even if it was used overseas, we took the view that we wanted to decarbonise it. And so we are decarbonising both the domestic and export sectors. We also took a scenario-based approach, and it's all solved through a sort of a lowest cost optimizer. So it's technology neutral in the sense that we didn't bias any of the technologies, but obviously studies are only as good as the assumptions that underpin them. And we used the AEMO, Australian Electricity Market Operators, ISP, integrated system plan for the majority of our assumptions. It was a project between the University of Queensland, the University of Melbourne, Princeton University and the management consultancy Nous. And for those of you who have or familiar with the net zero space, sort of followed on from the Net Zero America study, which pioneered this style of research. Okay, so what did we actually model? I've got an awful lot of information. All of it's publicly available. I'll put a link in the last slide for folks to, if you want to go and look at any of the stuff in more detail. But I think it's important to understand what it was that we modeled. The first aspect is that we modeled the entire economy. So it wasn't just the energy sector or the industrial sector. We looked at everything. And we could have taken a couple of different approaches to how we reduced emissions, but we're a relatively simple group of engineers and we like nice straight lines. So we took a linear reduction from where we are at the moment when the study started in 2020, about 600 million tonnes a year for our domestic emissions or national emissions, down to zero by 2050. And as I said, all of the emissions associated with our exports also need to be decarbonised on a 10-year delayed time frame. So from 2030 down to zero in 2060, noting that the size of the export emissions is double the size of our current national emissions. And then we took a scenario-based approach, which meant that we're not predictors of the future. I don't have a crystal ball and I'm not very good at guessing what's coming next. But so we looked at scenarios instead, all of which said we reached the target of meeting net zero by 2050, 2060, but there are different drivers that get us there. And so on the demand side, we looked at the lever of electrification. So in one of the scenarios, we looked at effectively electrifying as much as we could. So that meant the majority of the transport sector, all of the buildings and residential and commercial building sector, some parts of industry, so relevant to this to the HILT CRC and to this particular webinar. Decarbonisation across all the scenarios occurs through fuel switching from sort of fossil fuels to a clean hydrogen or a biogas, depending on the technology and where it's located. And also some synthetic liquid fuels, which might come from a biological source or be made chemically, but all of them from renewable CO2, and electrification. So fuel switching and electrification is the predominant sort of driver or transition that happens in the industry. So that's the rapid electrification that sees pretty much everything shift to electricity. On the flip side of that, we took a scenario that said, what if we can't or don't want to electrify as fast as the other scenario? So this has a slower rollout of electric vehicles, almost unchanged sort of rollout of building electrification. So still using a lot of or some gas, depending on the state, say Victoria, for heating and cooking in homes and businesses. That was the supply side. We can also then obviously look at levers on the demand side. That was the supply side. We can also look at levers on the supply side. One of which is to say, let's look at a fully renewables future. So let's stop the use of fossil fuels for all technologies, for all industry, for all sectors of the economy by 2050. And everything is provided through renewables. There is still some carbon capture and storage that happens in that scenario, as we'll see, but it's all associated with non-fossil sources, so sort of the CO2 that comes off cement production. That's specifically relevant to the HILT CRC. And then on the flip side of that, we said, well, we're already coming out of the back of COVID. We're, the war in Ukraine has all of these things have severely impacted supply chains. We're already starting to see communities being challenged by renewable energy rollout. So what if, for a combination of all these reasons, and perhaps some that we haven't even thought of yet, we can't deploy as fast as we want to? So what happens then? So in that case, we limit the rate of rollout of renewable build. So we can't build as much solar and wind as we want to. And in order to maintain the domestic economy and to maintain the energy value of our exports, there's a higher reliance on blue hydrogen, so hydrogen production using carbon capture and storage. So there's a lot more CCS. It's also relevant to heavy industry here in this particular scenario. And then the last one, which is the one that we want to that we'll try and focus on most for the rest of the webinar, is the onshoring scenario, which is the idea of bringing the production. So rather than sending our iron ore exports and our metallurgical coal exports overseas to be or in the case of a decarbonised world, our iron ore and our hydrogen carrier exports overseas to be turned into iron and steel on foreign shores. What if we did that on Australian shores? And likewise for the alumina and aluminium industry. What if we did all of the processing for that whole supply chain, bauxite, alumina, aluminium, on Australian shores? And so we focused on those two because they're the main ones. They're the two largest in terms of total emissions associated with the transformation of all of our mineral ores. And it's a very, very distant third. So the size of the third industry, which off the top of my head, I can't remember at the moment actually, but it was orders of magnitude less than an order of magnitude less than in the aluminium industry. So we focused on iron and aluminium. We didn't go all the way to steel. We took the view that steel production and all the various sort of nuances to steel production is very complex, and that Australia doesn't have vast expertise in that region or that area, and so we were better suited to producing pig iron that would then be exported. And it's the iron making where the vast majority of the emissions happen anyway. So that's the area where we're saving. Okay, so that's what we modeled. A little bit more, in terms of the onshoring scenario in particular for those who wanted, for these two industries. We transformed Australia's iron ore exports to pig iron, as I said, using hydrogen and a direct reduced iron process. And what we did was we took all of Australia's 870 million tonnes of iron ore that we export, and from 2030 we linearly swapped it out for DRI, such that by 2060 we were exporting no iron ore, and all of the iron ore had been processed into pig iron. The inputs to the process are pretty simple in terms of we're looking at hydrogen and electricity as the clean energy inputs. The diagram that I've got here indicates what we were looking to replace, which was the total amount of energy that would be used at the export location, is what was, so all of the efficiencies of the supply chain is what's gained by doing this on our shores. And so we've got the total energy input for how it would be produced overseas versus the total energy input for how it would be produced in Australia. And we did similar for the aluminium industry. We did the whole supply chain, bauxite and alumina, recognizing that the vast majority of our bauxite is already processed into alumina on Australian shores, but then we took all of the alumina that could have been produced and turned it into aluminium. And we used a combination of zero carbon electricity, inert anodes, and hydrogen for heat provision into both the aluminium and the alumina industries. And again, it was a linear transformation from 2030 out to 2060, such that all of our mined bauxite got converted to alumina, to aluminium on Australian shores. Okay, so that's the setup. That took longer than I expected, but what I would like to go through now is just some to highlight the impact of those assumptions. The study itself basically distilled all of our work down into 12 key insights across 3 key themes. We will focus for the rest of the time only on the looking at the heavy industry side of the slides. And as I said, there's plenty of information if you want and opportunity to ask questions around the rest of the study if you're interested. But in the interest of time, I'll skip on. One of the most impactful slides and impactful sort of outcomes from the study was actually mapping out what the infrastructure looks like, or the infrastructure build out looks like. And so, put quite simply, this is Australia in 2020. What you can see here is Australia broken with these sort of thicker grey lines into regions and states. We modelled 16 regions of Australia, and then spidery grey lines that sort of indicate transmission lines. And depending on how good your monitor is and how much you're able to zoom, you can see some little blue dots and maybe some little orange dots that represent existing solar and wind farms. So this is Australia as of today, let's say, close enough. And this is what the transformation to net zero looks like. So what you're seeing here are vast arrays of solar farms, these brown, goldy coloured parcels of land that are almost the size of Tasmania, crisscross with sort of blue transmission lines, larger transmission lines indicated in sort of the purple and magenta colours, and then a transformation of the southeast and southwest, upgrades to the grid, a lot more wind in the blue there, even some offshore wind, and smaller solar farms. That's for the general scenario. So just for let's electrify everything and let the model choose the options. The difference between this one and the onshoring scenario, and I might flick between the slides. So this is the overall net zero. This is what happens when we use the onshoring scenario. And what you can hopefully see is a reduction in the overall amount of build. And so that's what comes out of, that's the main thing that comes out of all of the assumptions, is that we need to build less stuff because we have to produce less energy, because we are not looking to transform materials overseas, we're transferring them onshore, and so we don't have to build as much infrastructure. The infrastructure is still predominantly solar. It's still focused around the export, and still largely focused around Western Australia. Located here predominantly for access to iron ore, although I know that there are other iron ore deposits around Australia that we might want to look at in future stages of the study, and also major iron ore ports. So that's the I guess this idea that we can export clean minerals or clean metal products rather than, or as well as, clean energy. So the total energy that we're exporting here between the two is the same. It's just that some of it's in a solid form. When we look at that in terms of some charts in terms of the overall amount of energy that's exported, you can see just how much gets taken up in the direct reduced iron, the DRI, and why there is such and the majority of it coming out of Western Australia. And you can see that the transformation there is smaller because we don't need to be exporting as much in the way of a clean hydrogen carrier. It's all in solid iron form. And you can also see the relative size. So the aluminium industry is in the blue there. So the relative size of the two industries there together. essentially the DRI dwarfs the others. Looking more generally at industry and the transformation across the sectors, I wanted to highlight the impact of electrification or slower electrification on the industry transition there. And effectively, so what we're focused on is this particular box, the third box down, associated with the energy mix associated with industry. In a case of high electrification, we see the majority of our sort of diesel and solid fuel products being replaced with decarbonised alternatives, some of which are hydrogen, or a good portion of which is hydrogen, and an increase, maybe a doubling of electrification of the sector. There's still a role for liquid fuels, but those liquid fuels, whether they're classed as diesel or oil products, are being synthetically made either from a biofuel or through chemistry like a Fischer-Tropsch process, so that they're not contributing to the overall carbon balance. If we take a slower electrification mindset, we can see that there's still, again, a role for it's a much smaller transition, and there is an increase in electrification. There is some hydrogen, essentially offsetting minor reductions in sort of those liquid and solid fuel products into industry, but there's also a lot of carbon capture. There's some carbon capture and storage associated with keeping those particular products decarbonised. Sorry, next slide. So one of the other, so I guess that's what the energy mix looks like in terms of the transformation, and what the infrastructure needs look like in terms of the transformation, both generally and specifically for the onshoring scenario. I suppose the other aspect that's of relevance to the HILT CRC and the potential audience today is carbon capture, utilization and storage, CCS. And it's a feature of our models and a feature of our modeling, in the sense that all of the scenarios require some level of carbon capture and storage, regardless of the overall energy mix that goes into it. And that comes about because we find that the land sector, so land use, forestry, agriculture, waste, land use change, all of that big, that encompassing of all of those sectors, we find that it approaches net zero but doesn't reach net zero but on its own by 2060. And so it's unlikely to be a provider of offsets into things like heavy industry. And that leaves really only carbon capture and storage as the only alternative to decarbonise some of these hard to abate sectors. And we see that here through the green line, which is the fully renewable scenario. We still see on the order of maybe a maximum of about 80 million tonnes a year, sort of steadying out to maybe 20 to 30 million tonnes by 2060. In all the other scenarios, including the onshoring one, the model chooses to adopt CCS quite readily, and the straight line base is basically where it hits the limit of what we've, our more conservative of the two limits for our injection capacity across 5 basins across Australia. The gold line that is heroically going up towards 1 billion tonnes a year is predominantly associated with blue hydrogen production. So reformation of natural gas and the CCS associated with that, primarily for our exports, for export of blue hydrogen, basically. And obviously, we're at the upper limit there of plausibility, feasibility, imagination, perhaps even at 1 billion tonnes a year across those 5 basins. But that's what's required to maintain our energy exports if we can't build renewables fast enough. I thought it's also useful to break down the sources of the CO2. And we can see that, so cement in the orange is a small but visible portion. There's also biofuels, and in the majority of scenarios, direct air capture, so capturing CO2 out of the atmosphere and storing it underground, is a feature of the modelling outcomes, both in the fully renewables case, the standard sort of vanilla scenario of high electrification, and in the onshoring case as well. It's the main CCS source of CO2. I thought I'd wrap up with a look at the impact of that change in infrastructure build and those assumptions on some costing outputs that come out of the model. The headline message is that we need somewhere between $7 and $9 trillion of capital out to 2060. The majority of that would be for the export industry, and so it's not something that we would be expecting Australian taxpayers to foot the bill for, although a portion, perhaps maybe 1/6 of it, it would be for the national economy, and so that's where I guess the bill comes back to Australia. I do have some other slides. I haven't put them in this pack that indicate for the national economy change percentage, total system cost as a percentage of GDP stays relatively constant in today's terms out to 2060, so that the transformation means that we're not necessarily spending a higher fraction of our GDP on the energy system. The standout here is obviously the onshoring scenario, where we're required to invest a lot less because the efficiencies of doing the processing onshore indicate that, essentially translate through to a lower overall capital spend. We don't have to build as much stuff. There's a slight change in terms of we spend more on industrial decarbonisation because of that iron and aluminium industries, but the headline there is the overall we spend less because we need to build less. I'll point out too that none of these, including the reference case, and our reference case, I should have said at the beginning, is essentially the Australian economy without any greenhouse targets in 2020, just sort of carried forward without any. It's not a prediction of business as usual. It's just the Australian economy in 2020 carried forward with GDP and population growth assumptions. What does that change in the amount of investment mean for the cost of abatement? And the standout here is that the cost of abatement, because we have to build less infrastructure in the onshoring scenario, the cost of abatement is about half what it is in the other scenarios, indicating that for nations who are looking to us to either provide them with clean energy or some sort of clean reduction agent, there's actual, some significant savings or significant saving potential by considering moving at least the iron industry onto Australian shores. That represents a lower, almost a half the cost of abatement than it does to simply keep taking our clean reducing agent, our clean hydrogen, and our mineral products. And so that all aligns with these with global decarbonizations and may well be in the interests of our international customers. Okay, so I'm looking to wrap up. I thought I would highlight the overall summary of strategic directions for the Net Zero Australia study, what we found out of it, the directions we should move in order to promote progression along these pathways, or at least something like these pathways. The the main one around options is that we need to accelerate all of the options that could make a material difference. And then relevant to this particular sort of highlight around heavy industry, we note that both clean energy and clean process minerals can and probably should be pursued as export opportunities. There are significant advantages from an overall investment and infrastructure build standpoint if we do the processing onshore and produce processed minerals. But obviously there are, other social and geopolitical parts of that puzzle to consider. And that it's really important that industry strategies and import replacement pathways be oriented towards what are our comparative advantages, which is a reasonably low cost of a clean energy or a clean energy carrier or a clean reducing agent. The rest of them there, I'll let you read for yourselves. There's substantial impacts and also substantial benefits from this transformation, and we should look to protect those members of society who are going to be most impacted by this transition, and that also, the transition will be coordinated through governments, but the majority of action will come through private investment or company investment, and that a significant portion of this piece is actually to rebuild trust that government institutions and businesses can do this transition. So with that, I would like to thank the sponsors of the study. So APA, Dow, Future Energy Exports, Future Fuels CRC, the Minderoo Foundation and Worley generously supported the project and guaranteed the project's independence. It wasn't a research, it was through philanthropic donations. I'd like to thank the advisory group and also highlight the folks involved in the study across the 4 institutions, and finally leave you with I guess a link there, the netzeroaustralia.net.au. If Google doesn't return it on the front page, which it should, then there's a link for you to find more detailed information about all of the sectors and more of the scenarios if you're interested. And with that, I'm going to stop sharing and hand back the microphone.
Thanks so much, Simon. I might ask Gus Nathan, our HILT Research Director, to come on now and join us for this panel session. We do have some questions in the chat, so please, if you've got any others, write them in there and we'll get to them in just a few minutes. But first of all, I thought I might pass to you, Gus, for your reflections on everything that Simon's just had to tell us.
Yeah, thanks, Jenny, and thanks again, Simon, for the great presentation and also the important work that's been undertaken here. I guess I'd like to make a couple of comments from the perspective of the HILT CRC. We think this work is really important, and also that it's an important, I guess, step in understanding where we go forwards, but also recognise that as per, there are lots of comments and questions in the discussion box around, what went into some of the scenarios, et cetera, and I guess, I've been discussing with Simon and also Michael and others, and we're looking to better understand how we can work together going forwards, because we see that really this is an important step, but there's a lot of other things we can then start to do looking forward, as Simon also alluded to in his presentation, of different scenarios. I think the approach of developing scenarios is really important. And I think that, going forwards, HILT has already started a lot of work, I guess, at the bottoms up end, looking at how industry can and potentially will transform from our industry stakeholder and regional perspective, whilst the Net Zero Australia is looking at the whole economy-wide thing. And we think there's a lot of opportunity to put these together going forward, and we're starting discussion towards that. I'll just share a couple of slides around some of the opportunities. If I can find out how to do it with this screen. Where are we? Different windows. Different box here. Doesn't seem to be showing my. I won't worry about sharing my screen. I'll make a couple of comments instead. I think what HILT is already doing is we're beginning to work on understanding how our sectors are prospective ways in which they will transform. So obviously, the work that's been done to date through Net Zero Australia, which is very important and a logical place to start, is to consider, what we already know about, for example, how green steel may be made. But of course, currently green steel is only made for about 3% of Australian ores. And then we see as the technology evolves, there'll be new pathways, and likewise for alumina, we see that to get to net zero, we need to do better than just simply bringing more expensive fuels into our current processes, but we need to be developing alternative, more effective, cost-effective ways of doing our processing with more circularity, more connections between our industries, which will help to offset these lower costs. And I guess these are the kind of things that we'd like to start, working on together. In the next stages is also better understanding putting together the work of understanding scenarios in which industry could transform with the wider whole of economy sections that's being developed. Already made a great start on that. So I guess from my point of view, this is a really important step. Demonstrates the scale of the challenge, demonstrates some key messages that Simon's put out really well. There's a lot of great detailed information on the website that Simon's alluded to, but also on top of that, what we're really keen to do is to then look at how to go forwards and build on that to better understand the next generation of scenarios that how the sector could transform as well. So Jenny, I think I'm going to hand back now to more discussion of the specific questions about Simon's webinar, but I guess Simon may also want to comment on some of the things that he sees going forwards as building on these first foundational things as well. So perhaps that's just an opening comment for him to give some reflection on some of the things he sees as being next steps, and then maybe we can go back to some of the specific questions that will come from the comments that people have made from the webinar summary. But thanks again, Simon, a great presentation, and appreciate the work.
Thanks, Gus. I guess really quickly, there's a lot more that we can do to dive into the heavy industry sector in particular. As I said, the majority, I don't want to get too technical on the modelling, but we're looking at the model looks at transformation of sectors, and so it assumes some, for a particular sector, this is the energy and the energy inputs required now, and here's the new efficiencies and new energy inputs later. And it doesn't really consider a pathway unless we specify it to. And we specified it for a couple of those, like the iron and the pig iron and the aluminium, and also for the cement industry as well. But there's a lot more work there to understand in terms of, it's a 2-year study, but it's in detail across, this is one aspect of about 17 different reports. So there's a lot of opportunity, I think, to build, to do some more rigorous modeling, more, incorporate more detailed understanding of precisely what the most prospective transformations of particular industries are, and then see those flow-on effects into the modeling. So for example, if I look at some of the questions in the chat there around why did we choose the iron ore deposits up in the north, it's not proven towards DRI technology, fully acknowledged there are ones down the south that might be better for it. That's the sort of question that we didn't have the opportunity to get into in this phase 1, and what we would really like, one of the aspects we would really like to get into in phase 2. The other one is that we don't have a crystal ball, and so we don't know what the world will require of Australia. And so we could have said it could be that the world needs more of our energy, more of our materials. Could also, in a decarbonising world, it could also be that they find other alternatives, or that the price of what we produce is too high, and so they purchase less from us. We kept it as of 2020 levels because, 6 of one, half a dozen the other. And so actually understanding that demand, the regional demand, and looking at those sectors in more detail, I think is another aspect that we'd really like to look into, that will then flow back into the overall results that we've presented here.
Thanks, Simon. So maybe just building on that and the questions that you pointed to there, Simon, there's a theme here around building in a sort of assumptions around technology that maybe isn't proven at scale yet. So maybe, Gus, if I can just ask you to maybe make a few comments about some of the work that HILT's doing about, producing green DRI from lower grade Pilbara ores, and also on the CCUS front and CCS front, just to illustrate examples of how this work ties together with the work that HILT's doing to solve some of these questions.
No, absolutely. And I think the points Simon made are all really good. I mean, there's a fantastic base here, but there's also opportunity for more things here. But obviously, one key element is that every process is bespoke and depends on the properties of the ore. And we know that the full net zero pathway is not fully proven, although there are some very important advances towards that direction, but they're also being made for very specific combinations of ores and systems which make most sense in one location or another. So what we're doing in HILT is we're working with our industry stakeholders and partners to understand which pathways and which sectors they think are most prospective for the ores that and also the markets they anticipate emerging. Then we're combining that with direct experiments of how those ores will operate in certain conditions, combined with process modelling, and we're looking also across not just iron and steel by itself, or alumina or bauxite through to aluminium by itself, or limestone through to lime and or cement by itself, but we're also looking at the connections between these industries. We think it's really important to develop a step change in circularity, and of course that's not just us. The world recognises the need for that. We need to make better use of things that are currently wasted in historic processes. So we think byproducts from the ore through to the final product will form new circular products into cement and lime. So we need to think all of these together, and we're beginning that process. And the more we start to do it, the more we'll get better understanding of some more specific scenarios, and that would be really useful then to feed into the kind of work that Simon and the team at Net Zero Australia are doing, to then start connecting the bottoms up with the top down, and feeding that into, and also the scenarios we develop through consultation with our partners and their stakeholders will also help to inform the scenarios, and back down the chain to consider it's a coupled system. So the more we can put the coupling between the energy and fuels locally and nationally and internationally, the better we'll develop more informed scenarios. None of them is correct, but they're all really important in helping the planning process. So I think that's some of the directions we're keen to push forward together.
Thanks, Gus. And Simon, maybe just on some of the CCUS assumptions, and how does the model take into account technologies that are still developing now in terms of S curves and things, and just maybe explain that a little bit further, sort of touching on the 3 CCUS questions there in the chat.
Yeah, so looking at them, so we included both carbon capture and storage, so just the straight capture and the storage, and there is also a component of utilization there, so some CO2, although not very much in comparison to the amount that's captured, is transformed into or is used to produce other products, sort of liquid fuels or gaseous fuels. The majority of it though goes towards goes to underground storage. In terms of, we took as best we could some industry specific costing assumptions around storage. So storage and transport costs detailed in our more methods. We've got a whole methods document. It's about 200 pages. The actual numbers are put into there. We check them with a variety of different experts. We acknowledge that CCS is a still deploying technology, but it is operating. You know, we've already got CCS operating in Gorgon. It's you know, there are challenges with its operation, and it's historically documented those challenges. But it is there. It is storing CO2, so in that regard, and I suppose the other aspect to it is that there are really only two ways that we can withdraw carbon from the economy, right? With two ways we can have negative emissions. One of those is from the land sector, and the other is from using CCS. No amount of renewable energy is going to, for example, take the CO2, stop the traditional production of, or the CO2 that comes off cement production. Right? Doesn't it's just part of the process. So if we can't offset it in the land sector, then we have to use something like CCS to do it. So fully acknowledge all of the challenges associated with the industry, but also I guess part of it is to highlight that it is necessary even under a fully renewables case, and probably why it needs some focus moving forward. In terms of adoption of things, yes, you know, they typically they typically take S curves rather than straight lines. And for things like the transport sector, we did that. So the adoption of electric vehicles and whatnot follows an S curve. But in the case of a lot of these technologies, you know, the difference is very, very small versus the ability to implement it in the model. And so we just went along with a linear transformation. That's clearly not the way it's going to happen. In fact, I would stress again that these are scenarios, not predictions. None of these scenarios are what's going to happen, and we don't endorse any of them. All models are wrong. Some models are useful. So the point is to highlight what they all show, and then, you know, start to have some of these more detailed discussions about it.
And there's a question here about sort of cost assumptions, and I think the assumptions in the model that leads to the result that the onshore processing scenario is sort of significantly cheaper by that sort of 2 billion amount there. So what kind of cost assumptions are in there for the energy export scenarios that's potentially leading to that result? And also a comment here about sort of, you know, Australia needing to remain competitive from a CapEx perspective versus other economies globally in order for that to happen, I guess.
Yeah, absolutely. And we you know, in the real world and the way this transition will happen, we will absolutely need to maintain that comparative advantage. In the modeling world, we have the luxury of being able to say the rest of the world is decarbonizing as well. And I guess our point was that relative to decarbonized energy and decarbonized products in other nations, we have no good, you know, we think it's very uncertain as to whether other nations will be able to produce these in the context of their own decarbonisation challenges, cheaper or more expensively than what Australia is. So, and it's the relative difference that matters. And so we basically took the view that our products will remain competitive. We calculated shadow prices and things that sort of, you know, highlight that, yes, the energy export cost is, levelized energy export cost is substantial. It's in the $30 to $40 a gigajoule by the time we get to 2060. Is that unrealistic in a decarbonised world? I think that's a step too far for us, you know, to evaluate at this particular point in time. So, yeah, I guess that's the assumptions. As I have said, they're all laid out in our methods, assumptions, scenarios, and sensitivities document. And yeah, in terms of the international competitiveness, it's a really great question, and one that we're not set up to answer at the moment. but would hope to look in more detail in phase 2. I should say, if anybody does have a crystal ball that tells us whether we're going to be competitive or not, we would love to hear, because it makes it easier for us to change the demand and along those lines.
So I'm just running out of time here, but I'm going to try to link 2 questions here that are not particularly linked, but I'll give it a go. There's one question about how's the model currently tracking today versus when the work was completed, and is it sort of on track, behind or ahead? And then just generally, how does the model optimize things like renewable energy locations, project locations? How does that, what's the coding like in the model for, and how does that work?
Yeah, so really quickly, are we on track? We are well behind, particularly when we consider, so the black lines here indicate, hopefully you can see my screen, the black lines here indicate where the historical maximum that we've ever done, and the rest of the charts indicate what we need to do. The only one that we have met really is the rollout of rooftop solar. Otherwise, we are well under what we need to do, particularly for solar. And then the second question was around how we actually optimized. So basically, we went around Australia and we looked at, we looked at Australia, divided it up into sort of 10 by 10 kilometre grids, evaluated the resource potential and therefore the cost of all of the technology on those grids. And then we applied a series of exclusion layers. Basically, the model cannot choose these areas to build from. Here, which are sort of illustrated on the slide here, they contain everything from mining, urban areas, water, defence, irrigated croplands for solar, so that we're not having this food versus fuel debate. And then also in purple are all of the critically endangered, and vulnerable species and ecosystems. And so the model can't choose to build in any of those regions. And so the rest of it is basically just a giant linear lowest cost optimizer to find the lowest cost solution within all of those constraints.
Excellent. Maybe just 2 very quick specific questions. There was one question about blue versus green hydrogen, and how is that accommodated in the model, and can blue switch out to green? And also, where are the 5 potential CCS sites? Are they all onshore or also offshore?
So I'll answer the first one first. The second one first. We took 5 main basins: the Surat, the Cooper, the Gippsland, and then the Browse and Bonaparte basins up off the northwest shelf. They were the main prospective ones that we looked at based on our discussions with all sorts of CCS experts and reservoir experts. And we took different injection limits depending on where they were. And that's sort of a map. Not only did we map the electricity flows, we also mapped the hydrogen flows and the CO2 flows around Australia. And that's sort of what you're seeing there. And your first question was around
blue versus green.
Oh, blue versus green, yes. So we let the model choose. We didn't put into it whether we had one or the other. The model, it was based on the cost assumptions. And so what we see in all the vast majority of the scenarios is blue starts being the most prospective initially, and then there is a switch around about 2040, 2045 to green hydrogen as the costs of solar batteries and electrolyzers continues to decrease. And so there's that crossover point in the 2040s where the blue production is phased out and the green production ramps up dramatically.
Excellent, thank you. Well, we've got 2 minutes left. Are there any final words, Gus and then Simon, to wrap this up?
Yeah, just like to make a final comment. Firstly, thanks again, Simon. It's been really great to see this work, and I think the discussion that's come here really highlights the importance of it and the opportunity to go forward. Just like to make one more comment, is that the kind of came out of the point Simon made at the end, is that a lot of the modelling that's done is based on current costs and current known technologies. we want to include scenarios where technologies improve and we get significant gains, both in how the processes run and also some of the emerging technologies that are not yet in this map. So they're the kind of things we'd also like to include going forwards. And just highlight again, thanks again, and we're looking forward to continuing to work together to better understand and explore new options. Also bringing in our stakeholders of industry and others to help better inform some of these scenarios that we look at.
Thanks, Gus. Last words from you, Simon.
Oh, just thanks everybody for your giving up your time to listen to our study today. I'm sorry we couldn't get to all the questions. And thanks for those who've I can already see some have reached out to me on email since the seminar's been going on. So happy to continue discussions as we go forward, and really looking forward to working with Gus again and the HILT CRC on phase 2.
Yes, thank you so much. And, like we've said, there's so much work that we're doing here at HILT that really ties in so nicely to your analysis as well. So thank you so much for Simon for being with us today. We'll send out a copy of the slides to everyone, and there's also the link to the recording. Simon, I'm sure, will be happy to answer any questions, as would Gus. And if anyone else is interested in finding out more about HILT, then please reach out to myself or Gus as well. But with that, I'll close off the webinar. Thank you so much for dialing in today.
Thanks, Simon. Thanks all.
Thanks.